Hi everybody. So the next chapter, we're going to switch gears here a little bit, right? The last chapter, chapter 7, was on quadratic functions. This particular chapter is going to be on exponential and logarithmic functions. So the basically the overall gist of the chapter, like I said, is to talk about these functions, and this may not mean a whole lot right now, but we'll talk about this obviously more later as we go on here. But so what we'll look at in this chapter is how to compose functions, and then we'll talk about functions that sort of do the opposite of what a given function does, and then we'll look at exponential functions, which are basically functions of the form y equals some number to the x power. So the thing that makes these different from say quadratic functions is, for quadratic functions, the x is in the base rather than in the exponent. And then we'll see that these exponential functions have functions that are sort of the opposite or the inverses. Those are called logarithmic functions. And then we'll look at some properties of logarithms. And then finally we'll look at how to solve exponential and logarithmic equations. So first of all, in this first section, let's first talk about composing functions and inverse functions. So basically when you're composing functions, normally if you have a function like, say, f of x is equal to, say, x squared plus x plus 1 or something like that, normally you'd put a number in for x, right? Like you'd have f of, say, 3, that would be 3 squared plus 3 plus 1, right, which would be, what, 13, something like that. Now what you can also do is you can actually put another function inside of a function. So maybe you've got another function like, let's say, g of x is equal to the square root of x minus 5, right? Now it turns out that you, instead of putting a number in for x, you can actually take an entire function and put it inside of another function. So it's kind of like one function is swallowing another one. And this may seem like multiplication, but it's really not quite the same thing. So we'll look at that first, and then we'll determine what a one-to-one function is, and then we'll see that if you have a function, sometimes you can find a function that does the opposite. Like, so for example, this function sends 3 to 13, the inverse function would send 13 back to 3, etc. And then we'll look at graphs of inverse functions, and we'll actually find the inverse of a function defined by an equation, the equation of the inverse. So let's look at composition of functions first. So to compose functions, you take a function and put it inside or into another function, just kind of like I was talking about. So let's say you have this function f of x is equal to x plus 1. Well, let's say you have another function g of x is equal to x squared. Again, what you can do is you can think of putting the x squared in for the x, right? So if I remember, whatever I replace that with, I have to replace that with. So if I replace that x with an x squared, I would wind up replacing that x with an x squared. So if I put this function inside of another one, I get x squared plus 1. And you'll notice that that is not the same as multiplication, right? If I had f of x times g of x, that would give me x plus 1 times x squared, which gives me x cubed plus x squared, right? And you'll notice here that it doesn't matter what order I add these in. Multiply them in, right? I'll still get the same answer. So now the thing is with function composition, you may not always get the same answer if you switch the order of composition, right? So if I put the function g of x into f of x, I get this. Well, let's reverse the order of composition. Let's put x plus 1 in for x here. So let's replace all the x's here with x plus 1. So if I do that, I get x plus 1 squared, which you might think is the same, but remember, again, this really means x plus 1 times x plus 1, so you cannot just square each thing individually, right? You can't just stick this 2 on that and the 2 on that, right? Because if you FOIL it out, right, you'll get x squared, and then you'll get an x, and then another x, you'll get 2x plus 1, so don't forget you'll get that middle term. So one thing about function composition is it's not commutative, right? You can, in some cases, you may get the same answer, but not always. And then notation for function composition is sometimes denoted by this. If you want to take the function g and put it inside the function f, right, you would write that. Now the thing I don't like about this notation is that looks too much like multiplication, so I prefer this alternative notation. But whatever you'd rather use. Sorry, this slide got kind of messed up here. So given two functions f and g, the composite function given by this notation I was talking about here before, you can kind of see it there, is f o g. And again, like I said, you could use this notation alternatively. So these two notations mean the same thing. Basically what you're doing is you're putting something into the original function, and then the output for the original function becomes the input for the outside function, right? So you kind of have an inside function g and the outside function f, right? So it's kind of like f is swallowing the function g. Right, so let's look at some more examples here. So let's say I asked, what's f of g of 3? Right, well, let's find f of g first. So f of g would be what I would get if I replaced all the x's here with x squared. So if I did that, I'd get f of g of x would be x plus 2 squared. So I just replace that x with x plus 2 minus 3, right? And if you work that out, you'll get x squared plus 4x plus 4 minus 3, which will give you x squared plus 4x plus 1, right? And so that's one way you could do this, is you can actually figure out what the composition is first and then plug the number in. So like if you plug in 3 for x here, right, you'll get 3 squared plus 12. So you'll get 9 plus 12 plus 1, which will give you 22. Now another way you could do it also is you could figure this out individually, right? Figure out g of 3. So in other words, put 3 in for x here. That'll give you 5. And then put 5 in for the x here. So that'll give you 25 minus 3, which will also give you 22. So you can actually do it either way, right? So let's say you want to find g of f of x. So in that case, I would just take the x here and replace it with x squared minus 3, right? And then just simplify. So I'll get x squared minus 3 plus 2, right? That just gives me x squared minus 1. So maybe look at a couple of other examples here. So let's say I want you to find f of g of x. So again, in that case, I'm going to replace all the x's in my f with whatever the rule is for g of x, which would just be x minus 1. And then that's basically the answer. Again, you can simplify that, obviously. You've got x squared minus 2x plus 1 if you FOIL that, and then plus 5x minus 5. So you'll get x squared plus 3x minus 4, right? And then to figure out f of g of 2, right, there's two different ways you could do that, right? You could either just stick, since we've already composed these, stick 2 in here. So that'll give you 2 squared plus 3 times 2 minus 4. That'll give you 4 plus 6 minus 4, which would be 6. Or if you prefer, right, you could figure out what g of 2 is, which would just be 1, right? Putting 1 in, or putting 2 in for x there, and then stick 1 in for that, right? So then you'd get 1 squared plus 5 times 1, which would also give you 6, right? So I don't know what's easier. I think, especially if you have to do this for lots of different values of x, I think it's easier to compose the function first and then plug the numbers in, but whichever way you do it, you should get the same answer. And then here I just want to reverse the order of composition, right? So wherever I see an x in g, I'll replace that with f of x, right? So I just get that, and then I guess I don't really need the parentheses there, right? So that should give me x squared plus 5 minus 1. So so that brings us to something else here, right? So we've kind of looked at composing functions. We'll come back to that more later. But one question you might have is, if you have a function, you know, can you find a function that does the opposite, right? Like kind of like I was talking about here before, right, where we had this function, say f of x equals x squared plus x plus 1, right? That function, if you plug 3 in for x, you'll get 13, right? So what you would want the opposite function to do, and the notation we're going to use for the opposite function is the little inverse here. Now that doesn't necessarily mean 1 over, so be careful. But that means we want to find the function that would say send 13 back to 3. So can we find a function that does the opposite of given function? And some of these will be sort of obvious. But let's talk about the notation here. So this is what's known as an inverse or an opposite function. So suppose that you have a function f, and g is a relation obtained by basically interchanging the x and the y coordinates of all the pairs in the original function. If g is also a function, then g is called the inverse of f and is denoted by that. And again, be careful, right? Don't confuse this with this notation. It does not mean 1 over. It means the opposite of, just like, for example, 2 to the negative 1 is the opposite of 2, because when you multiply that, right, you get, when you multiply 2 by half, you get 1. So that's why that notation is used. So basically, if you have a function, if you want to find the inverse of it, you just interchange all the x and y coordinates, and if after interchanging all the x and y coordinates, you also get another function, then that function is the inverse or the opposite of the original function. So let's just look at some functions defined in terms of ordered pairs here. So let's say we have this function that sends 2 to 6, right? So x goes to y, 5 goes to 4, 0 goes to 12, and 4 goes to 1. Find the inverse function, right? So what you'd like to do for the inverse function is just reverse this process, right? You'd like to send 6 to 2, 4 to 5, 12 to 0, and 1 to 4. And that's all you have to do, right? And then the domain of the inverse function is just the x coordinates, so 6, 4, 12, and 1. And the range is just 2, 5, 0, and 4, right? So like I said, for an inverse function, what happens is basically the domain and range, or the x and y coordinates of every point, just sort of swap around. Now you can also define a function in terms of equations, right? So let's look at, say, for example, the function f of x equals x cubed. You might even be able to guess the inverse for that. You know, what's the function that does the opposite of cubing? Well, that would be cube rooting. And one thing to notice here is that f inverse of x, right, does not equal 1 over x cubed. Right, because 1 over x cubed is not the same thing as the cube root of x, right? You could write that as the cube root of x if you want, right? And it's pretty obvious that those are inverses, right? Like, so for example, if this function sends 2 to 8, the inverse function will take 8 and send it to 2, right? Here's another function, right? If you have the function that adds 1 to everything you feed in there, again, what do you think the opposite function would be? Well, probably the function that subtracts everything there, right? And again, you can kind of check that by, you know, doing an XY table here and seeing if things sort of reverse here, right? So this would be for g of x, and this would be for g inverse of x. Now again, you can't test this for every point because there are infinitely many numbers in the domain of the function g of x, but you could test it for a couple, right? So like if you put 0 in for this function, you just get 0 plus 1, or 1, right? 2 will get sent to 3, 4 will get sent to 5, right? Each number here gets sent to one number more than it is by this function, right? So the inverse function should do the opposite, right? So if I put these as my domain values, right, I should get the corresponding range values over here. So if I put 1 in for x, 1 minus 1 is 0, 3 minus 1 is 2, 5 minus 1 is 4, 8 minus 1 is 7, right? So you can see the domain and the range swap around for the inverse function. Now, as far as graphs of inverse functions, it turns out that the graph of an inverse function is what you get when you flip the graph around this diagonal line. So let's say that you have some original function like this. Let's say this is your f of x. Then the inverse function will be what you get when you flip it around this diagonal line. So imagine that you have this line here and you take each point. One way you can do this is measure the distance here and then just go on the other side and make a dot. Measure the distance here, go on the other side and make a dot. Same thing here. Or you can just kind of draw it freehand if you're good at that. But so the inverse would look something kind of like that, right? So if this is the original function f of x, then this would be the graph of the inverse function, right? Because basically what you're doing is you're sort of swapping the domain and the range, right? Imagine that you're interchanging the x and y coordinates, right? You'd sort of flip it around that diagonal line, or the x and y axes there. So just remember that if you have some original function, the graph of its inverse, if it does have an inverse, will look like that. And we'll see that maybe not every function has an inverse. So that maybe brings us to another question, is which functions have inverses or opposite functions and which don't. We'll get to that eventually. But let's say that you wanted to graph these functions. to show that they're inverses of each other, right? I mean, if you were to graph this function, right, this would just be a straight line that goes through 3 on the y-axis, or on the y-axis, and has a slope of 2. So it's going to look like that. And so if you look at this function, right, you can rewrite this as x over 2 minus 3 over 2. That would be the function that goes through negative 1.5, and it has a slope of 0.5, right? So I probably should have slanted this one a little bit more, like that. So you can see those are mirror images around that diagonal line, at least if I was to graph it very well, right? This is just going to be the graph of x cubed shifted up by 1, so it's going to look like that. And then this is the inverse, right? This should be the graph of the cube root of x shifted 1 to the right. So remember, the cube root of x looks like that, so it's going to look like that. And you can see that those are mirror images of each other. Right, so maybe draw that a little bit darker. Here's 1, and there's the inverse. Okay, so that brings us to the question I was talking about is, does every function have an inverse? And it will turn out the answer to that is no. Only functions that are so-called one-to-one functions will have inverses. And basically, a one-to-one function is something where at most one x value is associated with a given y value. Right? So basically, what it means to be one-to-one, remember, a function will pass the vertical line test. A function that's one-to-one will pass what's known as the horizontal line test. Right? So each x can only get sent to one height. There are no two x's that are assigned the same height there, right? So a function is not one-to-one if it has like hills or valleys in it, right? So it can wiggle a little bit, but not too much. So if you think of the function here, y is equal to x plus 1, right? That's just a straight line, right? So that'll be one-to-one clearly. If you think about the graph of the cube root of x, right, that will also be one-to-one because there aren't any two x values that get assigned the same height, right? If I draw a horizontal line through the graph everywhere, each horizontal line will only touch the graph in one spot. So here's some curves here, and let me ask you which functions are one-to-one, right? Well, this function clearly can't be one-to-one, right? Is this one-to-one? Yeah, it looks like it. I mean, it's kind of hard to tell what's going on in here, but I'm not going to try to trick you, right? That looks like it's one-to-one. That's one-to-one, and this isn't even a function, right? Because it doesn't satisfy the vertical line test, or the horizontal line test. So, so I guess it is kind of one-to-one this way, but it's not a function. So the only one-to-one functions here will be that one and that one. So, so now that brings us to a question about, okay, so if you know the equation of a particular function, like let's say you know y or f of x is equal to 3x plus 1 over 5, and you know that it's one-to-one, how do you actually find the equation for the inverse, right? I mean, that might seem pretty obvious, but there's a lot going on here, right? Like you might know that the inverse, you're supposed to multiply by 5 and then divide by 3 and maybe subtract 1, but the question is, what order do you do that in? Well, it turns out that there's a handy procedure you can use for that, and that is the following, right? If your function is written in terms of f of x, just replace the f of x with y. That'll just make it easier to solve. And then interchange the variables x and y, and then solve this equation for y, so get y by itself, and then just to relabel it to make it clear that that's the inverse function, just replace the y with f inverse of x. And then we'll see later on that you can actually verify this result by using composition of functions. It turns out that if you compose inverses, if you stick a function inside of its inverse, you should always get x back. And the reason why is, if you think about it this way, right, the function f of x will take that function and assign it to some value y, and the inverse function will just send it back to where it came from. Right, so it makes sense that you should wind up where you started from. So let's look at an example here. So the question is this an inverse function? Well, this would be the graph of the square root of x shifted 1 to the right. All those transformations we saw in the last section that applied to quadratic functions, you'll see will apply to other functions. So it's just the graph of the square root of x shifted 1 to the right. Is that one-to-one? Yeah. So passes the horizontal line test. So just to make things easier, and you don't have to do this, but to make things easier, just replace this with y, and then interchange x and y, and then solve for y. So I want to get y by itself, so square both sides, and then just add 1 to both sides. So the inverse of this function is given by that. And again, if you're not sure if they're inverses of one another, just compose them, right? Take f inverse of f of x. If you do that, you do get x. And take f of f inverse of x. You get x there as well, so that proves that they are inverses, right? Now there is an alternative procedure for doing this, and that is, if you don't like that procedure, you can replace the function name with y again, and then solve that equation for x in terms of y, and then swap x and y. So the difference here is that for this one, you interchange x and y first, and then you solve. And for this one, you solve, and then you swap x and y around. So either way, it should give you the same answer. Maybe just go back and do this one that we just did here. Right, if I have y is equal to the square root of x minus 1, so you want to solve this equation for x instead. So square both sides, you'll get y squared is equal to x minus 1. You get y squared plus 1 is equal to x, and then swap x and y. Right, you'll get x squared plus 1 is equal to y, which is the same thing we got before. Right. So whichever method you prefer is fine. So let's look at this one, right? So you want to find the inverse of this, so just replace y with that, and I'm going to use the alternative procedure here. So swap x and y around, or sorry, solve this equation for x, I guess is what I did here, right? So I'll take y minus 4 is equal to 2x, and then divide both sides by 2. So y divided by 2, and then 4 divided by 2 is 2, so you'll get that. And then just interchange x and y, and that'll give you your inverse. So the inverse is x over 2 minus 2. And you can kind of, again, you should really compose them, but if you wanted to graph the function, that would be sort of another way to do it, right? This should be the line going through 4 that has a slope of 2, so it's going to look like this. And this should be a line going through negative 2 that has a slope of 1/2, so it's going to do something kind of like that. So they are mirror images, but the way that you'd really want to check to see if these are inverses again are compose them, right? So let's maybe just check this one. So if I do f of f inverse of x, right, what I'm going to do is I'm going to take my function f and just replace all the x's with this rule. So that'll be x over 2 minus 2. So I just take this x here and replace that with x minus 2 over 2 plus 4, and this should work out to be x, right? So if I simplify here, multiplying out, I'll get 2x over 2, so the 2's will cancel there. 2 times negative 2 is 4, plus 4. 4's cancel there, and I do get x, right? And then technically, you should really check the composition in reverse order. So if you do f inverse of f of x, in that case, you want to take this equation here, right, the x over 2 minus 2, and replace the x with 2x plus 4. So just reducing here, right, you'll get x plus 2 minus 2. If you add the 2's together, right, you do get x. So that does verify that those two are actually inverses of each other. So I guess we already kind of talked about this, but remember the one way you can know for sure whether two functions are inverses of each other is, again, compose the functions and see if you get x. I know we've done a couple of examples here, but let's just do some simple examples here. So we've seen before that x cubed is some function. Its inverse is the cube root of x, or in other words, x to the 1/3. Remember, that's the same thing as the cube root of x. So I guess the question is, if you compose the functions, do you get x, right? Well, let's take this function and stick the cube root of x in there, right? We're composing them. Well, the cubes and the cube root will cancel, so you do get x. Same thing if you reverse the order of composition. If you take x cubed and take the cube root of that, you also get x. Right? For this one, again, if you take this x and replace it with x minus 1, you'll get x minus 1 plus 1, which gives you x. Same thing here, if you take x minus 1 and replace the x here with x plus 1, you also get x, so that shows that those are inverses of each other. Okay, well, hopefully that's enough to give you an idea of what to do for that section. But if you guys need help, as usual, just let me know.